Welcome everyone. Today we have A-level physics paper 4 Feb March 2018. Another 2-hour paper, so this is going to be a long one. Now what I suggest is you should have solved the paper beforehand before coming to this video, and then you can see in the description below all the timestamps are given to each question, so just skip to the question where you are having trouble. Okay, so without wasting any more time, let's jump on to the first question. So, as with most question number ones, this also focuses on gravitational fields and circular motion, satellites, and all that kind of stuff. Part one here is asking us to state what is meant by the line of force in a gravitational field. Now, when you draw a gravitational field pattern around any planet or around any body, those patterns that you draw or the lines that you draw, what do they mean? What do they represent? That's what we are here to explain. And what they mean is actually that they're showing you the direction of the force which a mass in that field is going to experience. So if you were to just draw a force on a mass, it will be in the same direction as those lines. They could also mean one more thing, and it's that the path that will be followed by that mass in the field. So this is what the lines represent. Part 2 here is asking us by reference to the pattern of the lines, so the pattern that we were just talking about, near the surface of the earth. Explain why the acceleration of free fall near the earth's surface is approximately constant. So focus on the words that I've just highlighted, and basically they're asking near the surface of the earth we usually take the value of g as 9.81. So why do we do that? Like, even if you go, let's say, 100 meters above the earth, or 200 meters, or even let's say 1,000 meters above the earth, you will still take the value of gravitational field strength on earth as 9.81. So why do we take this as a constant value? We know that gravitational field strength is not a constant thing. The further you go away from the planet, the weaker it becomes. So that's the question. Why is it taken as constant? And if you zoom in on the earth, like from far out, if you zoom out, the field pattern looks like a radial one where all the lines are converging towards the center of the earth, and their distance between the lines, the spacing between the lines is changing. But as you zoom into the earth, you basically just see those lines as straight parallel lines which have equal distance between them. So that's the starting point. If those lines near the surface of the earth seem to be straight lines, then that means near the surface of the earth we can say approximately, and that's a pretty good approximation, that gravitational field strength's value also does not change. It is roughly 9.81, like near the surface of the earth, and by near I also mean by the, like, the top of Mount Everest. So even if you go pretty high, the value of gravitational field strength is not going to change that much. So if the field strength is constant, that means the force is also constant, since force depends on it, and since acceleration depends on force, so that is also going to be constant. Now for part B, we have a moon, and just saying that the radius of the moon is 1.74 kilometers. And now notice that the unit is kilometers. The mass of the moon is also given. You are just required to calculate the gravitational field strength at the moon's surface. So the formula for gravitational field strength is pretty straightforward, gm over r square, and the value of g can be found from page number 2 as always. Now you just need to use the mass of the planet itself, which is not the planet, obviously it's the moon, 7.35 times 10 to the power 22 kg. And for the radius, for the distance from the center of the moon, it's also going to be the radius of the moon, since you are at the surface of the moon. So the distance that you have from the moon's center is equal to its radius. However, you need to be careful with the units here. Since it's in kilometers, you need to convert it to meters first in order to get your answers in newtons per kg. So that's what we have done. We have multiplied it by 10 to the power 3. So for part 2 here, we have a satellite which is orbiting the moon, and they have given us the height of the satellite above the moon's surface. Now this is important. Why I've underlined it? Because it's the height of the satellite above the moon's surface. It's not the radius of the orbit which you're going to use in your formula. So keep that in mind. Now the starting point for these questions is always centripetal force is going to be equal to gravitational force. Since it's the gravity which is providing the centripetal force required for the satellite to continue its in circular motion. Now, most students will just usually skip to the formula that they have studied in class, but it's important that you show this working. I feel like it's also important not to memorize that formula because you can always easily derive it as we are doing here. So you can see that the mass of the moon cancels out. Oh, sorry, it's the mass of the satellite that cancels out. The mass of the moon is there in capital M, and then omega is basically just 2 pi over t. And then when you make t the subject of this formula, you can see that it's very easy to calculate. All you have to do is just plug in the values. The only thing that we need to be careful with here is the radius, which we have to enter in place of r. Now remember that the radius of the orbit is going to be the satellite's distance from the center of the moon. So not only do you have to include the height of the satellite above the moon's surface, but you also have to include the radius of the moon, since the sum of those two distances is equal to the radius of the orbit. So once you do that and you plug in all the values in your calculators, and you don't forget to cube r, and then uh, take the square root of the whole thing on the right hand side, you should be fine. And I don't think, yeah, this is a pretty common question, and it does repeat quite a lot. So yeah, we have our answer. So, for question number two, we are dealing with the topic of ideal gases. And you have 5.12 moles of an ideal gas at a certain pressure and a volume. And then you just have to determine the temperature. So, this is quite straightforward again. All you just need to remember is the ideal gas formula, which is PV equals nRT in this case. And you need to know that R basically stands for the universal or molar gas constant. The value of that is 8.31. You can always see that value from the second page of this paper. You don't need to memorize it. And then the other important thing is converting the volume from centimeter cube to meter cube. And this is where most of the students struggle. Converting centimeters to meters is quite easy for most, but when it comes to centimeter square and centimeter cube, they just need to remember that they have to also square or cube the multiplication factor in that case. So yeah, this is part A. Now, for part B, you are given a formula for the average kinetic energy of a molecule. Now, remember what I've underlined here, a molecule. So, this formula does not give you the kinetic energy of the entire gas. This is one of the biggest misconceptions that I've seen in most students. This is just the kinetic energy of one molecule. Now, the gas is being heated at a constant pressure, and so its temperature rises by 125 Kelvin, and we need to determine the new volume of the gas. So for part one, again, either you can use the above formula PV equals nRT all over again, or you can simply remember that when pressure is constant, then the temperature and volume are directly proportional to each other. So that's what I'm going to use here, since most of the students would know how to use the ideal gas formula again. So since volume and temperature are constant, their ratio is going volume and temperature are directly proportional to each other. Their ratio is going to be a constant. So therefore, I'm just doing using the formula V1 over T1 equals V2 over T2. And we know the initial volume and temperature. We know the final temperature as well. All you have to do is just add 125 to the older temperature. So then you can just find the newer volume here. Another thing to remember here is that the answer is required is in centimeter cube. So I don't need to use the I don't need to convert the volume back to meter cube first and then find it in meter cube and then convert it back to centimeter cube. However, while doing this, I kind of forgot that. And what I was doing was I was converting the volume back to meter cube and then found the answer in meter cube and then converted it back again. But with this solution, you don't really need to do that since these are just ratios, so their units actually just cancel out. So, yeah, we have the final answer here. Now, for part 2 here, we are required to calculate the increase in internal energy of the gas. And then it says further, it says that explain your working as well. So, what do we need to explain here in a calculation question? Well, you remember there are no forces between the particles in an ideal gas, therefore, it does not have any potential energy. So, usually the definition of internal energy is that it's the sum of kinetic energy and the potential energy of the molecules. But since we are dealing with an ideal gas, its energy is only going to be equal to kinetic energy and not the potential energy, since there is no potential energy of the molecules in an ideal gas. So once we have explained that, now we can just go ahead and calculate the increase in internal energy. When temperature increases, the kinetic energy also increases, and that increase in kinetic energy of the molecules is also the increase in the internal energy. Now, the formula for kinetic energy of a molecule is given above, 3 over 2 Boltzmann constant into temperature increase. Now I can put that there, and I can only find out the increase in internal energy of a single molecule. However, I need to do that for all the molecules, so I need to multiply this to the number of molecules in the gas as well. Now I know we have 5.12 moles, so if I know the number of moles, all I need to do is multiply it with the Avogadro's constant, which is 6.02 times 10 to the power 23, and that will give me the increase in internal energy of the entire gas. And if we don't make any calculation errors here, we should be fine. You can find the Boltzmann constant from page number 2, and yeah, everything else from here on is straightforward. So part C, part 1, says use your answer to the previous part to determine the external work done using the during the expansion of the gas. Now remember, whenever the volume of the gas changes, work is being done on the gas or work is being done by the gas. So in this case, since the gas is expanding, you should remember that it's the gas which is pushing the piston out or pushing the atmosphere away. So it's the gas which is doing the work. But in either case, finding the work done is done with the same formula. However, this formula has a condition that it can only be used when pressure is constant. So at constant pressure, when volume is changing, you just do pressure multiplied by the change in volume. Now all we need to look for is the initial volume and the final volume and find the difference of that, and make sure that you have them in meter cubes. Since we want to calculate our answer in joules, we also need to have our volume units as SI units. So once we have done that, we'll get to the answer of work done in joules. Now for part 2, the last part of this question, you can see that everything is coming nicely together, and now they just want us to calculate the heat required or the thermal energy required to heat the gas, which made it expand at a constant pressure. And this heat is represented as Q, and all of this is now coming nicely together to form the first law of thermodynamics. And the equation for that law is delta U equals to W plus Q. And it's very important to remember the signs, plus positive or negative, and the meaning of those symbols. So delta U is internal energy, W is work done, and Q is heat. Now all of these values could be either positive or negative, depending on whether they're increasing or decreasing. So delta U here is the increase in internal energy. Since the internal energy is increasing, we have to take it as positive. That's why I've specifically posted as a um, written with a plus sign with it, because it's very important to remember that work done here is going to be negative because the gas was expanding, and whenever gas is expanding, its own energy is going to decrease because it's the gas which is itself doing the work. So that is negative. And then once we solve and find Q, that is going to be 13300. Now, coming up on question number 3, this question mostly focuses on all different types of graphs. So, the first one is a graph of a simple harmonic motion, and the graph that you have to sketch here is velocity on the y axis and displacement on the x-axis. So for that, you really just need to remember two things. When you have the object at amplitude or at maximum displacement, then velocity at that time is always zero in simple harmonic motion. So the object is at rest. And when the object is passing through the mean position or the equilibrium position, then the velocity is maximum. So if you remember those two things, then you would actually see that you can plot 4 points on the graph. So those 4 points will basically be using these two concepts. So by using the first concept, we can see that when displacement is maximum, velocity is zero. So we have a point at x naught comma 0 and minus x naught comma 0, and then you have 2 points at 0 comma v naught and 0 comma minus v naught, which is the maximum velocity. And then most of you might not be familiar with this graph, but it's good to remember that as part of your preparation. But even if you don't, how do you join all these points together? Well, you just have to form a circle. So that was the first part. Part B is basically a graph of force versus the angle theta, and it's the angle between a current carrying wire and the magnetic flux density. So you should know while solving this question is the equation that you have to use is force is equals to magnetic flux density, which is B, multiplied by the current, which is I, multiplied by the length of the wire in the field, which is L, and then all of that is multiplied by sine theta, which is your angle. So if you remember the relationship between force and theta, you can see that the angle theta is basically a function of sine here. Now for that, I think what really would help is to remember the graph of sine theta. You should remember those graphs, let's say from simple harmonic motion, or if you have studied them in mathematics, then you should remember the shapes of those graphs. And they are those sinusoidal curves, which looks like a wave. However, one wave or one cycle of that graph completes over an angle of 360 degrees. Here you will see that the angle is only 90 degrees. So you only have to take the first quarter of that cycle. So starting from 0 comma 0, it will be a curve with decreasing gradient, and the gradient will actually become 0 while it reaches 90. So it's only a graph which goes from 0 comma 0 to 90 comma maximum force. But it's very important to remember that the gradient at the end becomes 0. So it's just the first quarter of that cycle. So part C of this question is dealing with another graph, and this time you have a sinusoidal power supply, which basically gives you an alternating voltage, and it has a frequency of 250 hertz and an RMS voltage of 2.8 volts. But in order to draw that sinusoidal graph, you need to know where the peaks are. So to find the peak voltage, you have to multiply the RMS value with under root 2 to find the peak value. So first you find that, and it's almost 4 volts. After that, you have the frequency which you will use to find the period of the graph. So basically, you need to know the time over which one cycle of the graph is going to complete. So from frequency, we can find the period, which is 0.004 seconds. However, if you look at the x-axis of this graph, it's in milliseconds. So convert 0.004 seconds to milliseconds, and you get 4 milliseconds. So one cycle of the graph will complete over 4 milliseconds. So I'll draw the peaks at 1 comma 4, and then from at 2 it will pass through 0, and at 3 it will be a peak at minus 4 or a trough, and then at 4 it will complete the graph, and then at 5 there will be another peak. So I'll draw this sinusoidal graph, and that is it. That's a very simple question. Okay, so part D deals with another graph, but this one is not actually a graph that you have to sketch or anything, but this is a graph of binding energy per nucleon on y-axis versus nucleon number on x-axis for all the elements in the periodic table. Now, about this graph, first of all, you should memorize this shape. You should know it to solve many of the questions in nuclear physics. Secondly, you should know that the peak of this graph, where I'm drawing a dotted line, is actually representing the element iron. And iron has a nucleon number of 56. So, iron happens to be the most stable nucleus, and it has the most binding energy per nucleon. Now, then, we only have to plot the 3 points for uranium, for barium, and for krypton. We know their nucleon numbers are 235, 141, and 92. So, first of all of them are greater than 56. So, all of them should be on the right hand side of that peak, more than iron. And secondly, uranium has the biggest nucleon number, so it should be on the rightmost. Barium is 141, so it's a little less than that, so a little to the left. And then krypton is 92, so it will be even more to the left. But all of them, since they are greater than 56, should be on the right hand side. And that's it. Okay, so we are going to begin question number 4 now. Part A is saying, explain what is meant by the natural frequency of vibration of a system. So, natural frequency is when a system is basically allowed to freely vibrate, or basically, by vibrating freely, what I mean is that there is no resistive forces, there are no external forces, there are no driving forces on the system. It's just the restoring force of the spring or whatever is basically making it vibrate back and forth. But there is no other force, no air resistance, no friction, no oscillator attached to it. That's what natural frequency of a system is. Okay, on to part B now. So, part B basically shows us a block of metal which is attached to a spring, and then that is attached to an oscillator. So, the oscillator, the metal, when it vibrates on its own, is gonna vibrate with its natural frequency. But when the oscillator is turned on, it is also going to provide a driving force, and that will have its own frequency, which we call the driving frequency. And that driving frequency is going to affect the vibrations of the metal block. So these are forced oscillations, and now it will not vibrate with the natural frequency but with the driving frequency of the oscillator itself. Now they have shown us the graph below that of display of the amplitude of the system versus the variation in the driving frequency of the system. So as you vary the frequency of the oscillator, the amplitude changes, and you can see that there is a peak at a certain point. That point happens to be where the driving frequency actually equals the natural frequency of this system, and we call this phenomena resonance. And that's what the first part is about. The first part basically asks us name the effect shown. So it's the resonance which is happening here. Now, if you go to part B or part 2 of this part, it says state and explain whether this oscillation, like, are they damped or are they undamped. So you see, when these oscillations are undamped, the amplitude actually can become very large, and by very large I mean theoretically it will just be infinite. The graph is actually just going to disappear of the top of the page, and you can't even see the peak, it will be that high. So theoretically that's what happens. But whenever you actually have a peak which is a little flatter like this one, it's not very very sharp, that means that you are dealing with a system where resonance is taking place but the system is slightly damped. And the more you increase the degree of dampening, the flatter and the shallower this peak actually becomes. So yeah, what we are going to write is that this system is damped, and the reason we are saying that is because the peak is not actually infinitely high. Now, the last part of this question says give one example or a useful example of this effect. So, what are the useful examples of resonance? Now, I suggest you should at least know 2 to 3 examples which you've actually studied in your syllabus. And I'm just going to name them, I'm not going to go into the details. So one of them is nuclear magnetic resonance imaging, NMRI, which you study in the topic of medical imaging. So that's where resonance happens when the radio pulses actually are at the same frequency as the frequency of precession of the nuclei. That's where resonance happens. And then there is another case where you have studied resonance, and that is also part of the medical imaging chapter, where ultrasound waves are produced or detected by the piezoelectric transducer. And that's where the ultrasound waves or the frequency of the ultrasound waves um, uh, produce compressions and rarefactions in the piezoelectric transducer, and they are actually becoming equal to the natural frequency of their vibration, which causes them to resonate and then basically detect ultrasound. Okay, so on to question number 5, and this question is mainly about ultrasound. The first part basically asks us to explain the main principle behind the use, and the focus is on the word use of ultrasound. So remember, there are two or three types of theory questions that you will see. So there is this type of question where they are going to focus on the use of ultrasound, and then there is the other one where they are going to focus on the production or the detection of ultrasound. So how are the ultrasound waves used to like make pictures of internal body structures? First of all, you need to focus on the word pulses. Pulses of ultrasound are transmitted, and you can't just say waves of ultrasound are transmitted. They have to be transmitted in pulses, because we need to be able to differentiate the reflected and the transmitted signal. So if they are continuous signals, then it's hard to identify them. That's why the ultrasound has to be in pulses. Secondly, whenever ultrasound is used, a gel is applied on the patient's body. It's called the coupling medium, and the reason for that is because the specific acoustic impedance between the skin and the air, they have a large difference. Therefore, the reflection of ultrasound is very large at the skin. So hardly any ultrasound will enter the body if the reflection is very large. So in order to reduce that difference, we are going to use the gel. Then the third thing that we are going to focus is that these pulses will reflect off different boundaries between the different mediums and different tissues inside the body. So, for example, between the boundary of soft tissue and muscle, there might be a reflection of ultrasound pulses, and that reflection will be detected. Then there might be an ultrasound pulse reflected from the boundary of muscle and bone, and so on and so forth. So, these reflected pulses are going to come back, and they're going to be detected by the same transducer which was producing them. So it's usually just a single device which transmits the pulses as well as detects the reflected one. Okay. Then these signals are going to be processed and amplified to be displayed on the screen. And then how do you use that reflected signal to get information about the boundaries or get information about the mediums? So there are two things here. First of all, it's the time between the pulses. The longer it takes for the pulse to reflect back to the medium, it means that the deeper that boundary is within the body. So the longer it takes, it means that the longer the distance is between the boundaries, and that is why it gives you the information about the depth of the boundary. The second thing about the reflected pulse is its intensity, how strong the signal is compared to the transmitted signal. So, if the signal is very strong, that means that a lot of reflection took place and hardly any of the ultrasound got transmitted through that boundary, which means that the specific acoustic impedance between the two mediums was the difference of specific acoustic impedance between the two mediums was large. But if the reflected pulse is very weak and a lesser amount of reflection took place, that means that the difference of z values between the two mediums, the specific acoustic impedance, was small, and that is why not a lot of reflection took place. Okay, so this was part A. Now we'll move on to part B, where we are simply required to define specific acoustic impedance. So this is very simple. You just have to remember the formula: Z equals rho multiplied by C. So Z is the symbol for specific acoustic impedance, rho is the symbol for density and density of that medium, and C is the symbol for the speed of the ultrasound wave in that medium. So you can write it down as a formula and then explain the symbols, or you can just write it down as a complete sentence that it's the product of density of the medium and speed of ultrasound in the medium. That simple. Now, part 2 of part B is asking that you have, if you have two mediums and both of them have their specific acoustic impedances, let's say Z1 and Z2. Now, the amount of reflection that takes place, or the intensity reflection coefficient that is there between at that boundary between the two mediums, depends on the Z values. So they're saying, how does it depend on the Z values? What if the Z values are very similar to each other, like they're almost equal? And what if the Z values are very different from each other, like if Z1 is much larger than Z2 or vice versa? Then what happens? So, as we were just discussing above, if the Z values are very similar, then the reflection is not going to be very large. And the formula that you can refer to is, for the intensity reflection coefficient, is Z2 minus Z1 whole square upon Z2 plus Z1 or whole square. And you can even plug in values of your choice. So enter two similar values of Z1 and Z2 and you will realize that it's close to zero. So hardly any of the fraction of the wave is getting reflected. And if you enter very different values, you will get an answer which is closer to 1. So it's also important to remember that this reflection coefficient cannot be greater than 1. The maximum value is 1 and the smallest value possible is 0. 0 means hardly any reflection and 1 means that most of the wave is reflected. So that's what we're going to write here. That's it. That's question number 5. Okay, so question number 6 is from the topic of communication, and this one is mainly about uh, analog to digital conversion and then back from digital to analog conversion. So ADC and DAC. And they've shown you a graph of an analog signal where the signal is in millivolts and the time is in milliseconds. And the sampling rate is given to you. That's important to note the sampling rate when we'll draw the next graph. So that's 0.25 milliseconds. And they're saying the 4-bit digital number system, the smallest bit or the least significant bit in that 4-bit system represents the last whole number 1 millivolts. Now we are required to write down or convert the value of the analog signal at 0.25 milliseconds and at 1.25 milliseconds. So at 0.25 milliseconds, you can see that the value of the analog signal is 5 millivolts. Now I need to convert this number 5 to the digital version or the binary system, the 4-bit binary system. So this is the trick that I use, or the method that I use to convert it, because I find it difficult to remember all the values myself. So all I do is just keep dividing the number by 2, and then if there is a remainder, I write it on the side. So, and if there is no remainder, then I just write a 0. And once you reach when you have divided and you can't divide any further, then you just go from the last number to the first number, so 101. But you can see that this is a 3-bit number, so how do I turn this into a 4-bit number? Well, on the left hand side you can just add another 0, and that will just convert it into a 4-bit binary number. So we'll do pretty much the same thing with 1.25 milliseconds as well. First, find the value of the analog signal from the graph, and this is somewhere around 8.4 milliseconds. But remember, since the digital signal or the 4-bit binary system can only represent it in whole numbers, so we need to round it off. It's also very important that you remember that when rounding off these values of analog signals to a whole number, you always have to round it down. So even if it was 8.9, I would have written 8 millivolts instead of that. Now, how do I convert 8 into a digital number? Again, just keep dividing it by 2, and there's no remainder, so write 0. And you can see that there are no remainders. In the end, we just get to 1. So 100 in that direction, 1000, that is our digital number, and this is already a 4-bit number, so I don't need to add any zeros to the left hand side. And this is how I will convert analog to digital numbers. Now, in this part, we are required to draw a graph where that digital signal is then converted back into the analog signal. So first the ADC converts analog to digital, and then the DAC converts that digital back to analog. But remember, since we have a limited sampling rate or sampling frequency, and we have a limited number of bits, the the analog signal will not be exactly the same as the original one, and there will be some inaccuracies or some compromises that we'll have to make. So it will not be that smooth as the original one. Now, how do we draw this? First of all, find the values of the analog signal at all the 0.25 milliseconds interval. Why 0.25 millisecond interval? Because that was the sampling rate of the signal. So I'll take the values of the analog signal at 0 seconds and then 0.25 milliseconds. Then I'm going to do it at zero point 0.5 milliseconds, and I'm noting down all the values from the y-axis, and then I'm going to do it at 0.75, 1 milliseconds, 1.25 milliseconds, and then 1.5 milliseconds. Once we have found all the values, we need to again consider that when they're converted into digital, you should remember that the digital signal was a 4-bit number, and it can only show the number to the nearest 1 millivolt. So we cannot go into decimals. So if, for example, you saw that at time 1.25 milliseconds, the value of the analog signal was 8.4, but I had to write it as 8 millivolts. So this is what we are going to do with all the signals where it is required. So all the values were basically whole numbers except the value at 1.25 and also the value at 1.5. The value at 1.5 was somewhere about 5.3 millivolts, so I had to round it down again to 5 millivolts. So that's where I'll plot the value of the new signal, and instead of plotting it at 5.3, I plotted it at 5 millivolts, and that's it. Then I'll just have to join all these points with straight lines. I have to draw these in steps. The width of each step will be 0.25 milliseconds because that was the sampling rate, and the height will obviously depend on their individual values. So just draw steps and just complete the graph. That is it. That's the question complete. Okay, on to question number 7, part A. State what is meant by electric potential at a point. So this is going to be defined very similar to gravitational potential. We have defined gravitational potential in one of the previous one or two past papers as well. So, what is electric potential? It is essentially work done or the amount of energy on a unit positive charge. So, unit means 1 coulomb of charge and it has to be positive. So, we need to basically choose one convention. So, we just go with positive charge. And then, what do we have to do with that positive charge? You have to bring it from infinity, from very far away, to a point in a field. So that will be electric potential at a point. Part B is going to show us two spheres. Both are charged. One is metal sphere A, the other one is metal sphere B. Now the distance between the centers of these two spheres is 44 centimeters. Notice the unit, it's in centimeters. You might have to convert it later. We don't know, but still it's important to notice whenever the distance are anything other than SI units. Then you have basically a point P, an imaginary movable point between the two spheres, and the distance of point P is being measured from the left hand side, so from the center of A. And then they have given you a graph of electric potential, the combined electric potential of these two metal spheres. So potential times 10 to the power 4 volts is on the y axis, and distance from A is x in centimeters, is shown on the x axis. Now, the first question asks to state and explain whether the two spheres have the same charge or the opposite charge. Well, if you come and look at the graph, you will notice that the values of V are always positive. Now, remember that a positive charge have positive values of V and a negative charge has negative values of V. So, if they were opposite charges, we have to subtract them, positive value and a negative value. So, the value will transition from a positive value to a negative value as you go from A to B. But here you can see that the value starts positive It maybe decreases a little bit somewhere in the middle, but as you go closer to B, the value starts becoming more positive again. So what does that mean? That both of them are actually positive charges. Not do we only know that they are same charges, but we also know that they are positive charges. Although the question is not asking us whether they have a positive or a negative charge, they are just asking us whether whether the charge is of the same sign or the opposite sign. So we can just write, well, the charges are of the same sign, and we know for a fact that these two must be positive charges because the potential is always positive. If there were two negative charges, then the potential will be an exact, the graph will be an exact mirror image of this below the x-axis, and it will be a potential which will always be negative. Anyways, now on to the next part, which is basically saying that a positively charged particle, so we have a test particle now, and we are going to move it freely from surface of sphere A to the surface of sphere B. Describe qualitatively the variation, if any, with distance x of the speed of the particle. So as it goes from A to B, this positively charged particle, what is going to happen to the speed of that particle uh, at different positions in this journey? So if you come back to the graph, you're going to notice that this is the graph of potential. Now, potential energy is definitely proportional to potential, electric potential. So you can see that from the beginning of the journey around x equals 12 centimeters and to x equals to 25 centimeters, the graph is basically going down. So potential is decreasing. And since potential energy is proportional to that, we know that potential energy is also decreasing. Now, if potential energy is decreasing, then what is it converting into? Obviously, it's converting into the kinetic energy of the particle. So in this first part of the journey, the speed of the particle is going to increase. However, we need to go one step further and also look at the gradient of the graph. Now, you will notice initially that the graph is much steeper. So, the potential energy is dropping much quicker compared to later on in that graph, where you can see if you draw the tangent that the potential energy is dropping slowly. So, speed is increasing, but it is increasing at a decreasing rate. So acceleration is basically decreasing. That's the first part. Now, what happens when it passes at 26 centimeters? So you come to the graph and you will notice that that is actually the lowest point of the graph. And at that part, you will see, since this is a stationary point of a graph for math students, you know that you call it a stationary point. The gradient of the graph, if you draw a tangent, is zero. So that means that at that time, for that particular moment, the potential is not changing. Potential energy is not changing, which means that there is no energy being converted to kinetic energy. That means that at this time, the speed is not changing. Now, on to the next part, which says between 27 centimeters to 31 centimeters. So after 26 centimeters, after the lowest point, you can see that the graph is going up now. So potential is now increasing, which means potential energy is increasing. Now, how is that potential energy going to increase? Because there is no other forces acting here, and it's only a rest particle, a positive particle moving freely here. So it means that the only way that potential energy can increase is from the kinetic energy of the particle. So kinetic energy is going to decrease, which means that the speed is going to decrease. Again, look at the gradient of the graph. Initially, it's much shallower, and then afterwards, the graph becomes much steeper. So this time, the speed is decreasing, but at an increasing rate because the gradient is increasing. Now, the last part asks you what happens to the speed when it reaches the surface of sphere B at x is equals to 32 centimeters. There you're going to notice that the graph, when it reaches x is equals to 32 centimeter, is still not flat. It becomes flat after that when it hits the surface, but when it is arriving at the surface, it's not going to hit the planet at a speed of 0. It will have some speed. Secondly, the speed is actually still decreasing because the potential is still increasing. So that's what we're going to write. The speed is not zero, and the speed is still decreasing when it reaches the surface of B. So that was the first part. Now, the next part is saying that the particle that was moving between A and B has a charge of 3.2 times 10 to the power minus 19 coulombs. And the mass of the particle is also given. They want us to calculate the maximum speed of the particle. Now, this is very important, the maximum speed of the particle. Notice what do we what did we write down in the previous answer? Where was the speed of the particle maximum? Well, it was at x is equals to 26. So it's the energy conversion between the surface of sphere A and then x is equals to 26 centimeter, where the speed of the particle was increasing. And at x is equals to 26, the speed is going to be maximum. So you need to go back to the graph, and then you need to see what was the potential of the graph at x is equals to 26. So it was around 1.43 times 10 to the power 4, of course. You don't forget that, the power which is given in the graph. And then you can also see the value of potential at the beginning at x is equals to 12 centimeters, which was 2.14 volts times 10 to the power 4 volts. So you have the values of potential between these 2 points. Now, how do you find the speed? Well, the first thing to realize is that it's the potential energy which is converting into kinetic energy. So, and there is no other type of energy involved. Initially, the kinetic energy was also zero, so we don't have to worry about subtracting kinetic energy, because we only will be subtracting zero from the final kinetic energy. So, yeah, we can say that the change in potential energy is equals to the change in kinetic energy. Now, change in potential energy is found by finding the change in potential and then multiplying it with the charge of the particle in question. So we have the change in potential from the graph, and we have to multiply it with the charge of the particle. That's potential energy change. That will be equal to kinetic energy change, which is half mv squared finally, and then minus zero because initially it was at rest. Now, the only thing unknown in this entire equation is V. And we have the mass of the particle, we have the charge of the particle. We have found the difference of V values from the graph, and we plug it all into the equation. If we don't make any calculation mistakes, we should get to the right answer, which is 8.3 times 10 to the power 5. Okay, so question number 8 focuses on operational amplifiers, and the first part is asking for the definition of infinite bandwidth and infinite slew rate. Now, I always say to my students that for operational amplifier, at least for the theory part, for the definition parts, you should just focus on memorizing them rather than trying to understand them too much in depth. So infinite bandwidth means that all the frequencies are equally amplified, or the gain of all the different voltages of different frequencies is the same. Now, infinite slew rate basically means that when you make a change to the input voltage, that change, the response to that change in the output occurs immediately without any time delay. So the focus here is on the word change. Okay, so this is part A. Now, part B is basically asking an ideal operational amplifier circuit is given to you. And if you have prepared this chapter, you should know that this is actually a comparator circuit where the input to both the inverting and the non inverting inputs are compared. And if the inverting input is larger, which means the minus input is larger, then the output is also going to be negative. And if the non inverting input is larger, then the output is going to be positive. So, part one asks determine the resistance of the thermistor at which the output is zero. Okay, so when is the output of a comparator circuit zero? Well, it is zero when V plus and V minus are equal to each other, which means that the inverting input and the non inverting input should be exactly the same. Now, how is that possible? For that, you really just basically need to look at the connections of the two inputs. Both of these are potential dividers. In one potential dividers, we have the thermistor and a fixed resistor of 800 ohms. And in the other potential divider, we have two fixed resistors of 1.8 and 1.2 kilo ohms. Now, when we want the inputs to be exactly the same, that means that we want the ratio of both of these potential dividers to be exactly the same. That way, that 4-volt potential difference between the 0-volt line and the input will be divided equally, and or in exactly the same way in both potential dividers. So that way we will get the same input at inverting and non-inverting input, and that would mean that you can form an equation from where you can find the resistance of the thermistor. Another way you can solve this question is by using the potential divider equations on both the potential dividers on the left hand side. Now, obviously, this will take a little more time and a little more space, but it still gives you the right answer. And I think it's this one is a little easier to understand. So, use the potential divider equation on the branch where we have two fixed resistors, and you see that the non inverting input will turn out to be 1.6 volts. Now we already know that V out has to be 0, which means V plus and V minus should be the same. So my V minus is also going to be 1.6 volts, and if I know that, I can also make a potential divider equation for the other branch where I have the thermistor. And once I make that equation, the thermistor resistance is unknown, and when I find that, it turns out to be 1200, the same answer that we got from the other method as well. So this is part 1. Now we can move on to the other part. Here they're saying that the temperature of the thermistor is gradually changed, and this will also change the resistance of the thermistor. So initially what we had was the resistance of the thermistor at exactly the value RT, which was 1200. Now when you decrease the resistance of the thermistor or increase the value of the thermistor, that will change the conditions of the potential divider, which will also change the output voltage. So we'll come back to our comparator circuit and we'll just go back to the basics here. So remember that in a comparator circuit, what we are doing is we are simply comparing the input voltages at V plus and V minus. If V plus is bigger, you're going to have a positive output, and since the and if V minus is larger, we are going to have a negative output. And these output values are always equal to supply voltages. Why is that? Because the amplifier always saturates, since the gain of the open loop gain of the amplifier is very very large, somewhere around the order of 10 to the power 5. Now when the resistance was equal to RT, the value in the previous part, the output was 0. We already knew that. We have already done that calculation in the previous part. But when the resistance drops below RT, what happens is that the value of V minus becomes greater than V plus. And in this condition, as already discussed, the output is going to be negative. And since the supply voltage is plus and minus 9, so this is going to be negative 9 volts. Now, what happens when the resistance of the thermistor becomes greater than the value that was in the previous part, the value RT? When that value is larger, what happens is the value of V plus, which is the non inverting input, becomes greater than the value of V minus, which is the inverting input. And in that condition, as already discussed, the output is going to be positive 9 volts. So now we have all our conditions. We can see that at the resistance RT, the output is going to be 0 volts. At the condition when the resistance is less than RT, the output value is going to be minus 9 volts. And when the resistance is greater than RT, the output is going to be plus 9 volts. So now we can plot that graph. Make sure that the line crosses the 0 value when it is crossing the resistance RT. But for all values less than RT, it's going to be minus 9. And for all values bigger than RT, it's going to be positive 9. And the value of the operational amplifier output cannot be greater than these plus 9 or minus 9 values, because it is the value at which it saturates. So we're going to make two straight lines, one at minus 9, one at plus 9, at the values which are other than RT. and at RT the value is going to exactly cross the zero mark, and that's it. That's the entire graph. Now, part 3 is saying draw a symbol for an LED connected at the output of the circuit such that it emits light when the resistance of the thermistor is less than RT. So, if you've got the previous answer right, and if you've understood what has happened in the comparator, we already know that when the resistance is less than RT, then the output is minus 9 volts. It's a negative output. And when the output is negative, the current flows in the opposite direction. So we want the LED to be emitting light and to be conducting current only when the current flows in the opposite direction. And for that, the LED has to be connected in the opposite direction, right? Second thing that you need to remember that is anything that you connect to the output should be connected between the output terminal and the 0 volt line. So keeping these two things in mind, you can go back to your circuit above, which is figure 8.1, and that's where we have to draw it. So just take a connection from the output voltage and then join it to the 0 volt line or the earth. And then all you have to do is make the symbol for an LED which should be conducting current in the opposite direction. Now, a slight mistake that I have made is I have not drawn the arrows that are coming out of the LED. So make sure you draw those as well. I have basically missed out on those. So make sure you draw those. All right, on to question number 9 now. So this question focuses on the topic of Hall voltage from the chapter magnetic fields. We have a thin slice of a conducting material. Electrons enter the material from one of the faces, and remember that these are electrons and they're not positively charged particles but negatively charged particles. What we have here is then the magnetic field, which is going from top to bottom, and they're saying name the two faces where the Hall voltage is going to be developed. So, in order to do that, what you should remember is what happens to the electrons when they enter the slice of the conductor. So, because of the magnetic field going from top to bottom, the electrons are going to experience a perpendicular force and they are going to be pushed to either the side PSVY or QWRX. So, keeping in mind that the electrons are negative, we'll apply the left hand rule, and then whatever answer we get from the left hand rule, we are going to take the opposite of that. So what we get is the direction of the force towards the face QWRX, which means that QWRX is going to become more negative and PSVY is going to become more positive. So those are the two faces where an electric field is going to be set up, or you can say a Hall voltage is going to be developed. And this also answers the question to the second part, which says state and explain which of the two faces named in a part 1 is more positive. And as already shown on the diagram above, it's PSVY which is more positive. And how did we get that answer? We used the left hand rule to identify the force on the particles. But remember, left hand rule is made for positively charged particles. Our electrons are negatively charged particles. So wherever your thumb is pointing, you have to reverse that answer. And that's why we got the direction of the force that we got. So we have answered both the questions in part A. Now let's move on to part B, which is basically saying the Hall voltage expression is VH equals to BI over N multiplied by T multiplied by Q. So B is the magnetic field, I is the current, N is the number density of charge carriers, T is the thickness of the conductor, and Q is the charge on the charge carriers. So they're saying use the letters to identify the distance T. Now I'm gonna digress here a little bit. I can give you the answer right away and I can tell you the trick. But what's really important is that you remember how this expression was derived. So we're gonna take a bit of time here, although it's only a 1 mark question, but it's very important to understand the concept of Hall voltage. What we'll do is from start to finish, we're going to understand how it is developed and how did we come to this expression. We're going to derive the expression from start to finish. So what happens is when the electrons are pushed to the side that is shown, An electric field is set up between the faces P, S, Y, V, and Q, W, R, X. And the electric field goes from the positive to the negative side as shown by the green arrows. Now, an electric field is also applying a force on the electrons, but that is going to be in the opposite direction to those green arrows since electrons are negative, and the magnetic field is pushing them on the other side. So both opposite forces, when they become equal to each other, that's where we are gonna start our derivation. Two forces are equal to each other. Electric field force is electric field strength multiplied by the charge on the electrons. Magnetic field force is basically given by the formula B into charge of electron multiplied by their drift velocity. Now, you should remember that the formula for drift velocity is I is equals to A and VQ, which you have already studied in AS physics. And that formula is also, by the way, given on the third page of this paper. So from there, we make V the subject and we substitute it into the equation in place of V. And then what happens is you can see that the equation is already starting to form in the final form that we have already seen on the next page. Now, what you need to remember is that the electric field strength, the uniform electric field strength between the two faces of this conductor, will be the voltage between the two faces divided by the distance between the two faces. So that distance is shown with the blue arrow on the conductor, and VH over D is going to replace E in the formula. Now, one more thing that we need to realize is that the A in the formula is the cross sectional area of this conductor. And that cross sectional area happens to be the area from where the electrons are entering the conductor. So that cross sectional area is basically a rectangle. So you just have to multiply two dimensions. One of the dimensions is D, and the other one is what we call T. So that was the T which you had to identify in that question. Now you will replace A with D into T, and you can see that when you do it, um, D from the equation in the numerator and the denominator cancels out. And when you make VH the subject of the formula, you get the exact equation which was already given to you in the part B. So now we know what T is. T is that thickness of the T is that thickness of the face from where the electrons are entering. But then T, which T are you going to take? The vertical one or the horizontal one? That could also lead to confusion. So always remember that this T is the one which is parallel to the magnetic field lines. So see, the magnetic field lines are vertical. Therefore, the RT is also going to be the one which is vertical. Secondly, you can also remember that it is perpendicular to the direction of the movement of electrons, and it's on the same phase from where the electrons enter. So remembering those two things, you can narrow down your dimensions to the one which you have to identify. But it's always good to remember the entire derivation, and if you understand that fully, then these questions are not really hard to answer. Anyways, part 2 is asking to state the meaning of the symbol n. Well, you should know that it is called the number density of charge carriers. In this case, those charge carriers are the negative electrons. So we can also say the number density of electrons. But I think you should go one step further and also explain the meaning of density. Density basically means anything which is available per unit volume, per meter cube. So we can say number density, or it is better to say number of charge carriers per unit volume. So part 3 is saying state and explain the effect, if any, on the polarity of the Hall voltage. So right now we had a Hall voltage where the front facing side was positively charged and on the side which was on the other side was negatively charged. What will happen to this polarity if instead of electrons you had positive charge carriers entering from the same side and entering in the same direction? So let's just clear up this diagram and then see what will happen. Now remember, how did we came up with the polarity of those two faces in the first place? We used the left hand rule. So we're going to use this again, but this time it's quite simple because you don't have to reverse your answer. You just have positive particles entering from this side. And when you apply the left hand rule correctly, what you will get is your thumb pointing towards PSVY, which means that the positive particles are pushed to this side. So this side will become more positive and the other side will become more negative. So did the polarity change? No, it did not. Even though we have positive particles now entering instead of electrons, because the positive particles have an opposite charge and they are pushed to the opposite side as well. So somehow the polarity just remains the same. So, unless you change the direction of the particles altogether, changing the sign of the charge carriers is not going to change the polarity at all. Okay, so that was question number 9. Okay, question number 10 now. First part says define magnetic flux. So, magnetic flux is just a product of two things. One is B, the other one is A. B is your magnetic flux density, which is calculated in Tesla. The other thing is your cross sectional area through which that magnetic flux is passing. Now, if you're just writing B into A, that then it is necessary that the area and the magnetic flux density should be perpendicular, should be normal to each other. That means they should have an angle of 90-degree between them. But if you are just giving a general equation where you don't want to write that it should be perpendicular to the area, then let's just take a general situation where the area and the magnetic flux lines are not perpendicular to each other. Then you could give two different answers. So, one is the situation where you would take the angle between the normal to the area and the magnetic flux lines. So, if this is the angle that I'm taking, then I'm going to write BA cos theta. However, if I change this angle to the plane of the area and the magnetic flux line, then this, instead of cos, I'm going to write sine theta. So this will become B into A into sine theta. Okay, moving on to part 2, state Faraday's law of electromagnetic induction. I feel like this definition or this law repeats every single year. I seriously think it does. I've not done the proper analysis, but I think it does. They basically just repeat every single paper. So you should just memorize the whole thing. EMF induced is proportional to rate of change of magnetic flux linkage, which means that the change of magnetic flux linkage divided by time. Okay, so part B shows us a solenoid connected to a DC power supply. So that means a current is going to pass through a solenoid and it's going to produce its own magnetic field. And then around that solenoid, we have another coil which is named C, and it has 96 turns and it's wound around the solenoid. Now, there is a uniform magnetic flux in the solenoid, and that is given by the expression which is shown on the page. Now they're saying calculate the average EMF induced in C when a current of 3.5 amperes is reversed in a time of 2.4 milliseconds. So EMF induced is again going to be found by the Faraday's law, but this time you need to use the equation of the Faraday's law. So that is change in magnetic flux linkage. So number of turns time the magnetic flux over time. So we have 96 turns. We'll write that in place of n. For the magnetic flux, we are just gonna just use the equation given above. Now in that equation, it's the current which is actually changing. And how is it changing? Focus on the word reversed. Remember, it's a DC power supply. DC power supply gives you a constant steady current. But since they are reversing the current, it's the current flowing of 3.5 amperes in one direction and then it goes in the opposite direction. So, what is the difference between these two currents? Well, it's actually going to be 7 amperes since they are in the opposite direction. So, difference between 3.5 and minus 3.5 is 7 amperes. And I'm going to do that calculation in brackets for I. So, once we are done with that, we are just going to divide the whole thing by time, which was 2.4 milliseconds. So write that down in seconds. And then once you calculate the answer, you will get your EMF in volts. which is 1.9 volts. Now, part C. The DC supply in figure 10.1 is now replaced with a sinusoidal alternating supply. So this time around, you have an alternating supply, so which does not give you a steady current. It's a current whose direction and value keeps changing. So they're saying what kind of EMF is now going to be induced in coil C. First of all, you don't have to reverse or switch on or switch off the DC voltage because alternating changes by itself. But the shape of the graph of the induced EMF is also going to be a sinusoidal alternating voltage. So, first of all, we need to say that the EMF induced will also be alternating. Secondly, we need to say that it will have the same frequency as that of the alternating supply because the number of time the alternating voltage completes its cycles in, let's say, in the second, the same number of times or with the same frequency will have our EMF induced changing its cycles as well. So they're basically, although they're slightly out of phase by 90 degrees, they will have graphs which are exactly the same shape. They will have their own different peaks and they will be slightly out of phase, but they will have the same shapes and they will have the same frequency and the same time period. So that was the second important point. Question 11 shows us some energy bands of a solid. Now, in a solid, you have, or in any material, you have three types of bands in the outer shells. It's the valence band, it's the last band where the electrons are actually bounded to the atom. Then you have a forbidden gap where the electrons, it's the energy level where electrons cannot exist. And then you have the conduction band when, if there are electrons available in that band, then they are going to conduct electricity and, that material has a lower resistance if there are more electrons in that conduction band. Now they're saying that the width of the forbidden gap and the number density of the carriers in each of the bands depends on the properties of the material. So in part A, if you have a metal, why does the why does the resistance of a metal increases as its temperature increases? That's what we need to answer. So for a metal, the first thing that you need to realize is that they actually have no forbidden gap, and that's because the conduction band and valence band kind of overlap, so they are like one and the same. It's not like electrons are going to jump from the valence band and go into the conduction band and then the number density is going to increase. No, it does not happen because they are overlapping, so they're basically just sharing electrons. Now what happens is, since there is no forbidden gap, when you give energy to the electrons by increasing the temperature, they don't actually it doesn't actually increase the number density of electrons in the conduction band. That pretty much stays the same. However, increasing the temperature has the effect of increasing the lattice vibrations of the atoms as well. So increasing temperature is going to increase the vibration of the atoms, something that you have been studying since O levels or maybe even before that. And what does that do is it makes it hard for the electrons to travel through the lattice, and that will increase the resistance of the metal as the temperature increases. So in the part B, we have not a metal, but this time we have a light dependent resistor, an LDR. And these LDRs basically behave in such a way that when you shine light on them, when light intensity increases on them, their resistance decreases. So that's what they're asking. Using the band theory, explain why does that happen. So first of all, you need to realize what material LDRs are made out of. They're made out of intrinsic semiconductors. And semiconductors are a little different from your metals, which we have just discussed above. So where in metals we had no forbidden gap and the valence and the conductions band were overlapping, in semiconductors you actually do have a forbidden gap. Now it's not like total insulators where the forbidden gap is very large. Here the in the semiconductors the forbidden gap is there, but it is small enough that it can be overcome. That amount of energy can be overcome by the electrons if they are given the right amount of energy. So what happens when light shines on these electrons on the semiconductor? The electrons absorb these photons of light and they gain enough energy to be promoted from the valence band to the conduction band. Now remember, it's the conduction band where the conduction of electricity actually happens. So you have a greater number density of electrons in the conduction band that is going to decrease the resistance. Also, in semiconductors, when electrons leave their place in valence bands and go to the conduction band, holes are also left behind. So holes are just absence of electrons in the valence band, and they basically act as positive charge carriers for the intrinsic semiconductor. So you have number density of charge carriers increasing overall, because there are more electrons in conduction bands as well, and now there are more holes in the valence band as well. So both these things lead to a decrease in the resistance of the LDR with increase in light intensity. Okay, the second last question of this paper, question number 12, is about X-rays. First part says, give two reasons for the lack of sharpness of an X-ray. So how do you make the X-rays sharp in the first place? That's what you need to understand. Well, two things that are very necessary for the X-ray to be sharp is that the X-rays need to have high energy, so their frequency must be large and their wavelength must be short. We call them hard X-rays, and the low energy X-rays are called soft X-rays. So that is very important that you have high energy X-rays. So one of the reasons could be for the lack of sharpness could be soft X-rays, X-rays with low frequency or low energy. Another reason is that when you have that target metal anode, if the area of that metal anode is too large, then what happens is it creates very large partial shadows which make the images blurred and not very clear, not very sharp. So the target metal anodes need to have a smaller area. If that area is too large, that will create larger partial shadows. Another reason is that the X-rays might get scattered, and for that we need to have a lead grid or an aluminum grid. Now when that is not there and the X-rays get scattered, that will also lead to a lack of sharpness in the image. So part B shows you a cross sectional area of a metal, and parallel X ray beams are passing through this sheet of metal. Now, this metal sheet happens to have two different thicknesses. The top part has a thickness of 3.2 mm, but the bottom part thickness is not given to X and it's just written X there. Now, the linear attenuation coefficient for X-ray beam in that metal is 1.5 per centimeter. It's important to remember that this is given in per centimeter, but the thicknesses are given in per millimeter. Whenever you use the formula for attenuation of X-rays or ultrasound, it's very important to remember that the units for mu, which is the coefficient, and the units for the thickness, which is X, must be consistent with each other. Now they've given you the ratio of the intensity of X-rays that pass through the 3.2 mm thickness and then passes through the other unknown thickness as well. That ratio is 0.81. So by applying the formula in the numerator as well as the denominator, we can make that ratio using the equation for the attenuation. So I've written I naught times E to the power minus 1.5 times 0.32. Now, why have I written 0.32 here? Because I've converted millimeters to centimeters in order to make the units consistent. In the denominator, I have the same formula again, but this time I don't know the thickness. It's the same material, so it has the same value for mu, but I don't know the thickness. And this entire ratio between these two thicknesses is going to be 0.81. So I naught and I naught, which is the incident intensity, cancels out, and then all we have to do is rearrange this equation. Now I know that many students tend to have problem with while solving these exponential equations, so I'm going to show each and every step. So first of all, I'm just going to make e times 10 to the power minus 1.5x the subject and calculate the right hand side using my calculator. Once I have done that, all I need to do is apply natural log on both sides of the equation. So that will be ln e to the power minus 1.5x, and on the other side I'm going to have ln 0.764. ln 0.764 can be calculated using my calculator, and ln e is equal to 1, and the power shifts down to become the coefficient. Now, all I need to do is just make x the subject, and I have to divide minus 1.5 on the other side with ln 0.764, and my calculator gives me 0.18. Now, remember, we converted the x or we converted our distances in centimeters. So, this was in centimeters. However, the answer is required in millimeters. So, I've written 1.8 millimeters. Let's move to part 2. Ratio of intensity is also the ratio of powers. You should know that because intensity is just power per unit area, and they're saying calculate the ratio in decibels. So decibels is basically just a unit for calculating the ratio of powers, and that is calculated by the formula 10 log base 10 and over the two powers. So the two powers that we have, P1 over P2, we already know the ratio. So we don't need to insert the actual values of power into the equation because their ratio is already known to us, which is 0.81. We're just going to insert that into our calculator, and what we'll get is negative 0.92 decibels. Now, many students might get confused by the negative sign, but remember you have to include the negative sign. It is the right answer. Just remember that whenever inside a log or a natural log you have a number which is less than 1, you're always going to get a negative answer. So remember that the power in the numerator was having a smaller value than the power in the denominator. That's why the ratio was less than 1. And whenever the ratio is less than 1, the actual ratio, then the ratio in decibels is going to be negative. All right, we are on to the last question, question number 13. This will focus on nuclear physics. First part says to define the radioactive decay constant, which is basically lambda. You should remember that it has a symbol of lambda. And this is just the probability of decay of a nucleus divided by the time. So it's probability of decay of a nucleus per unit time. All right. Part B says that we have a relationship between decay constant and half life, which is given to you. Now, this is one of the equations which you should memorize, but you should also know how to derive the equation. That's what we have to do. We have to derive this equation here, and the starting point will be the exponential decay equation, which is the final number of nuclei left and the number of initial nuclei times e to the power minus decay constant into time. Now, when time equal to 1 half life passes, the number of nuclei left in the radioactive sample will be equal to half the value of the initial nuclei. So n will be replaced by n naught over 2 in the equation. And in place of time, you are now actually not going to write the variable t, but you will replace it with the symbol for half life. Okay, then n naught and n naught cancel out, and you will be left with 1 upon 2 on the left hand side. After that, all you have to do is apply natural log ln on both sides, and then ln e is going to become equal to the 1, and the power is going to shift down to the coefficient. Then what you need to realize that whenever you take the reciprocal of the function inside the log sign changes. So I have ln 1 over 2 right now, but if I make this ln 2, so if I take the reciprocal of 1 upon 2, the ln will have a negative sign instead of a positive sign. So that is what we'll do in the last step, and you can see that we come out with the exact equation which was we have to prove. Now, in the last part of this question, we have a small solution which contains a radioactive isotope, sodium 24. The entire solution had an activity of 3.8 times 10 to the power 4 becquerels. Now, sodium 24 decays into something else, which is a stable isotope, and the half life of sodium 24 is 15 hours. You note the time in which the half life is given, it's very important to keep the units consistent. Now, this solution, the entire solution, is poured into a container of water. So now you have a huge container of water in which the entire solution is poured. So for this container of water, we know the initial activity. Then we let 36 hours pass, and then we take a small sample out of that entire container, which is only 5 cm cube. So remember, you had an entire container of water whose initial activity was 3.8 times 10 to the power 4, and then we took a small portion after 36 hours from that entire container. And after 36 hours, that small volume had an activity of 1.2 becquerels. And we are supposed to calculate the entire volume of water in the container, which had that initial activity which is given to us. So let's just look at the whole thing visually. You have a container which has a large amount of water. We don't know how much it is, but we know its initial activity. And then from that container, we take a small amount of water, which is just 5 cm cube. And we know the activity of this small sample, but we don't know the initial activity. We do know, however, the final activity after 36 hours of this small sample of 5 cm cube. So, first of all, I'm going to use the equation for radioactive decay on this small sample. All right. And that equation is final activity equals initial activity multiplied by E times 10 to the power minus decay constant into the time that has passed. Now remember, I know the final activity. The final activity of this small sample is 1.2 becquerels. So that's what I'm going to write in place of A. However, I don't know A naught, which is the initial activity of this small sample. Then for decay constant, I don't know this in the equation yet, but I can easily calculate it from the formula that we just derived or that is given to us in the above part. So that is going to be ln2 over half life. The half life is given as 15 hours, and if you use that, you will find out the value of the decay constant, which is going to be 0.0462 for decay constant. We can plug that into the equation, and then all we need to do is plug in the value of time as well. Now remember, decay constant is per hour, so time also needs to be in hour, which is given to us as 36 hours. We plug that into the equation and we find the initial activity of our small sample to be 6.33 becquerels. Now, remember, this is the initial activity of the small sample. Then what will be the initial activity of the large container from which this small sample was taken? Well, all you need to do here is very simple mathematics where you can just use ratio. So just ask yourself this question. If the initial activity for 5 cm cube sample was 6.33 becquerels, then what will be the initial activity or what will be the volume of the sample that has a large activity of 3.8 times 10 to the power 4 becquerels? So I just cross multiply, I solve that ratio, and I get my answer to be 30016 cm cube, which I'll just write down to two significant figures. So that becomes 3.0 times 10 to the power 4 cm cube. Okay, so that was it. Hope you got value out of the entire video. You got your problems sorted out where you were having trouble with some questions, and hope the explanations were clear. Now, feel free to look through the channel, feel free to look through the suggested videos. I have also solved some of the other entire past papers as well. And since there are very few days left in your exams now, so yeah, feel free to look through the past papers and look through the questions where you are having issues, and I'll see you next time.